Okay, so last video I showed you how to draw your ionic molecules. Today we are going to start looking at how you are going to draw your covalent molecules. So majority of this unit does definitely surround your covalent molecules. Really important to make sure that you have sorted out how to draw electron dot diagrams or Lewis diagrams for your covalent molecules. And that's because we're going to build off of it. So this is kind of the starting point for all the different diagrams that we do. We start with dot diagrams. From those, we talk about how we can do structural diagrams. And then from there, we talk about three-dimensional shape. And then we use three-dimensional shape to help us determine intermolecular forces, melting points, and boiling points. So this is a unit where it's really important to make sure that you understand the stuff that happens at the beginning of the unit, because if you struggle with it, what winds up happening is like in a couple of days, it becomes really overwhelming because you're really not sure how to do this because you're still struggling with this piece, okay? So really important to make sure that you spend the time practicing and that you feel pretty comfortable with drawing out your covalent molecules. So first step, like we talked about the other day, is just going to be to decide that it is actually going to be a covalent molecule. I'm going to decide that because when I look at what type of atoms are in my molecule, I'm going to see that they're all nonmetals. And that's going to be my indication that I want to draw a covalent molecule and not an ionic molecule. So when we are drawing covalents, the reason these look different is we're not moving electrons like we did in the ionics, right? We're not gaining and losing, we are sharing. So we have to find ways to share electrons and ensure that all of our atoms have a full valence shell, which is going to be 2 for hydrogen, 6 for boron, and 8 for pretty much everything else that we are dealing with, okay? So I'm going to show you 2 different ways that you can go about doing these. Some of you really like one way, some of you prefer the other way. It's really up to you. There are definitely some steps that are going to be similar in both methods, which is going to have to be with determining what goes where, so looking at your molecule and determining what goes in the middle versus what doesn't. So that's another big difference between covalent molecules and ionics. Not only do we have different things happening with electrons, we also have very different things happening with the placement of our atoms. Right? When we did ionics, we were kind of just putting them all in a line, or maybe we were bending the line. That doesn't happen in a covalent molecule. They don't tend to go in a line. Usually what we find is we have one atom that goes in the middle. Because it goes in the middle, we call it the central atom. And then usually most of the other atoms are attached to that central atom, okay? So how we're going to identify the central atom, I really should have put a slide in here for that. Okay, so how we're going to decide it. So we need to identify the central atom. So the central atom is going to be the atom that goes in the middle of our molecule or our drawing. We identify the central atom because it is the atom with the most unpaired electrons. Because it has the most unpaired electrons, that means it wants to make the most pairs. So we're going to kind of look at what our molecule is, we're going to look at the different atoms that are in it, and from there we're going to decide what goes in the middle just by looking at how many valence electrons each one has. And then based off of how many valence electrons each one has, we should be able to decide how many pairs it has the potential to make. So figure out which one has the most unpaired. That is going to go in the middle of your diagram. Everything else, for the most part, is going to just go around it. So you're going to place things either above, to the right, below, or to the left, right? And you'll see as we go through shapes a little bit more, sometimes we'll use some different options. But usually those are kind of where we're going to start when we are doing our Lewis diagrams for positioning those non-central atoms. If ever you find yourself in a position where you have multiple atoms that have the same number of unpaired, so a really common one is sulfur dioxide. Okay, and when you guys tend to hit SO2, you look at it and you're like, well, they're all in group 16, so they all have 6 valence electrons. So a couple of different ways how you can determine that sulfur is going to go in the middle. Okay, one of the ways is generally our covalent molecules tend to want to be symmetrical if it's possible. The way that I can make something symmetrical if I have an S and two O's is I can put an S in the middle and I can put an O on each side, right? Then I go O, S, O, I wind up with something symmetrical. The other way that I can figure it out as well, and I don't want to say this is an always rule because it's not an always rule, but when you get into bigger molecules, you'll see that it'll often give you the central atom first and then provide to you what is attached to it afterwards, okay? Doesn't always hold true. We definitely have some molecules where that is not the case, but in some, probably 75% of the time, that is going to be the case. And you'll see when we start getting into molecules that have more than one central atom, they'll often go in an order where it will be central atom, then what's on it, then the next central atom, and what is on that. Okay, don't worry too much about it now. We'll definitely work our way up to examples like that. So, determining the central atom is always going to be a step, regardless of which of the two methods you end up choosing to work with. Once we've selected the atom that goes in the middle, we put the others around it, and then that's where we're going to use one of either of these two methods. So, the one I find you guys tend to use more frequently is method 1. So I want to say that this is the first worksheet that you have on covalence in your bonding booklet. And I think why most of you guys like this method more is it's easier to figure out how many pairs of electrons you are sharing to get that full valence, okay? So this one tends to be a little bit more of what I call a math way. And usually because most of you in chemistry are good at math, usually this tends to be the way you pick, but there are definitely some people that tend to choose method number 2, which is more, I guess I would call it like a visual manipulation type method. They both get you to the exact same picture at the end. They just go about doing it in a different way. So when we are doing the first method, so I'll kind of walk you through what each of these blanks mean, and then we'll look at an actual example. So for the first method, which is kind of the math way, the first thing we want to do is we want to determine how many valence electrons we actually have. And that's because this determines how many dots are going to go into our diagram. Okay, so to get this, I'm going to look at what group are they in on my periodic table, and then I'm just going to figure out from there how many valence electrons they have, and then I'm going to add up all the atoms that are in my molecule, and I'm going to determine how many they have. Okay, the next line says number for full octet. So this basically means if I wanted to give everything a full valence shell, how many electrons would I actually need to be able to do this? So I'm going to look at the formula that I have. For every atom that is not H or B, I'm going to count it as wanting 8. So if I have CO2, I have a C and I have 2 O's, so I have 3 atoms, none of which are any of the special ones. So I have 3 atoms wanting 8, so 3 times 8, I would say that I have 24 would be the number for the full octet. Okay, so number of bonding electrons. So how we figure out the number of bonding electrons, it's just going to be the difference between the number for full octet and the number of valence electrons. So if this is 24, and this was, let's say, 20, I'm going to do 24 minus 20, and it's going to give me 4. So that's telling me that 4 electrons have to be shared for me to be able to fill the valence shells. Okay, then the last step is determining the number of bonds. So when it comes to bonds, you have the option of a single bond, a double bond, or a triple bond. The difference between them is how many pairs of electrons you are sharing. So in the case of a single bond, I am sharing 1 pair of electrons. So there would be a pair of electrons drawn between 2 atoms. If it was a double bond, I'm sharing 2 pairs of electrons. So I would have a pair and a pair, or 4 electrons drawn between those 2 atoms. If it's a triple bond, then I would have 3 pairs, okay? So Where this is going to help me with respect to the number of bonds is I'm going to be able to determine what kind of bonds I should be drawing. So I would start by drawing single bonds into all of the openings between atoms. If that gets me to how many bonds that I have written here, then I don't need any double bonds. If it doesn't, then I'm going to have to start to add some in. Okay, so now that I've kind of walked you through the method, let's look at an actual example. So we have SHF, okay, that is our molecule. So I'm going to first decide if it's ionic or covalent. In this case, I'm going to decide it's covalent because I don't have any metals inside of it. The next thing I need to decide is how am I actually going to place these three atoms. So I need to decide what's going to be the central atom. So sulfur is in group 16, which means it has 6 valence electrons, which means it has 2 that are unpaired. Then I have hydrogen, it's in group 1, so it has 1 unpaired electron. So far sulfur is going in the middle because it had 2 unpairs. Hydrogen had only 1 unpaired. When we get to fluorine, it also only has 1 that is unpaired. So how we're going to put this together is we are going to put the S, that's not an S, we're going to put the S in the middle. We're going to put the H on one side, and we're going to put the F on the other side. Okay, you could have swapped the H and the F around. You could have put one on top and one below. You could put one on top and one to the right. It really doesn't matter yet. Okay, later in the unit it will matter, but for now, really what we care about is figuring out which one is going to go in the middle, and then the other ones are just going to get placed around it. So, 2 seconds. So now that we've decided on the orientation of our atoms, the next thing we need to do is actually start to figure out how many electrons and stuff we have. So we're going to start at number of valence electrons. So do you need a calculator? No, you don't need a calculator. Do some of you like to use a calculator? Yes. We are all guilty, myself included, of sometimes doing really random things when we add numbers and subtract numbers, where we do something and we come up with an answer and then it's like, no, that's totally not the right answer. So I would always say there's no shame in using your calculator to make sure that you have the right number down. There's nothing wrong with choosing not to use it as well, but make sure that you have done your math right, okay? So number of valence electrons. What we're going to do for this is we're going to figure out how many dots our final diagram is allowed to have. So sulfur, we said, had 6 valence electrons. Hydrogen had 1, and fluorine had 7. So when we add 6 plus 1 plus 7, we come up with 14. So our final diagram is going to be allowed to have 14 dots in it. So number for full octet. This is what we said. We would go through our atoms. Everything that's not hydrogen and boron, we count as wanting 8. Hydrogen we're going to count as wanting 2, and boron we're going to count as wanting 6. So I have sulfur, it wants 8. I have hydrogen, it wants 2, and fluorine, which wants 8. So 8 plus 2 plus 8, that is going to give me 18. So to get the number of bonding electrons, we're going to get the difference between 18 and 14. So 18 minus 14 gives us 4. So we need to have 4 bonding electrons. To determine the number of bonds, there's always 2 electrons per bond. So we're going to take the number of bonding electrons, which is 4. We're going to divide it by 2. 4 divided by 2 gives us 2. So we know that we need to have a total of 2 bonds. So now what we're going to do is we're going to go to our diagram and we're going to start by drawing single bonds, right? We talked earlier about how you have single bonds, doubles, or triples. So a single bond means a shared pair. So I'm going to draw a single bond between the sulfur and the fluorine, and I'm going to draw another one between the sulfur and the hydrogen. So now when I look at it, here is one bond, and here is a second bond. That matches up with the number of bonds that we knew we would need to have. So we don't need to draw any double or triple bonds. Okay, and we'll look at some examples in a bit where we do. So the next thing we have to do is, now that we've figured out the bonds, we need to fill in the valence shells. So We have fluorine. We know fluorine wants 8. Right now it has 2. So we're going to give it a pair on top, a pair on the left, a pair on the bottom. Okay, that now gives my fluorine 8. Then we go to sulfur. It has 2 and 4. So we need to give it 4 more. So a pair and a pair. Okay, we always draw them in as pairs. We're never going to draw them in as singles. Okay, then we get to hydrogen. So remember, hydrogen only wants 2 valence electrons. It already has 2 from this shared pair, so I don't need to add anything to it. So if we've done everything right, what we should find now is that we have 14 dots in our diagram. 14 dots because that was how many valence electrons we are actually allowed to have. If I have more than 14 or less than 14, my picture is not good. I need to go back and I need to fix it and figure out where I went wrong. So we want to make sure we have 14. So 2, 4, 6, 8, 10, 12, 14. We have 14 dots, so that is good. And then the last thing we want to do to make sure that we've done it right is we want to make sure that everything has a full octet. So we look at fluorine, it's got 8 around it. We look at sulfur, it has 8. And then we have hydrogen with 2. So this is a relatively simple molecule because everything went in as a single bond. And we didn't really have to do anything fancy. So let's look at a different one. So we're going to try the same method again. So we have CF2S. So same as last time, I have to decide which atom is going to go in the middle. So carbon has 4 valence electrons, which means it has 4 unpaired. Fluorine has 7, which means it only has 1 unpaired. So far carbon's winning the race for the middle. Then we have sulfur. It has 6 valence electrons, so it has 2 unpaired. So again, it's still going to be the carbon that goes in the middle. So we're going to put the carbon in the middle. This time though, we have 3 things that we have to place around it, right? We have 2 F's and an S. So I'm going to put an F up here. I'm going to put another one here. And a little more to the side. There we go. And I'm going to put an S right there. Okay. So carbon in the middle. It's our central atom. Everything else goes around it, right? I only had 3 things to place, which is why I only did it like that. If I would have had 4, I would have thrown 1 more over here. But in this case, I didn't. So now that we figured out where we want to place things, and again, if you were doing this question on your own, you could have rotated it, and that would be totally fine too. There'd be nothing wrong with that. So number of valence electrons. We have carbon. It wants 4. Then we have 2 fluorines at 7. And then we have a sulfur at 6. So we have 24 valence electrons to play with. Okay, so our final diagram is going to have 24 dots. So number for full octet. I have no hydrogens and I have no borons. So everything is going to want 8. So I've got a carbon, I've got 2 fluorines and a sulfur. So I have 4 things all wanting 8. Which means 4 times 8 is 32. So my number for full octet is 32. To get my bonding electrons, I'm going to do the 32 minus 24. And I come up with 8. Okay, number of bonds, we're going to do 8 divided by 2, which is 4. So same as last time, we start by drawing singles. So well, I don't want red, hold on, back to black. So it's 1 pair, 2 pairs, 3 pairs. Now we've put a bonding pair between each set of atoms. So that gives me 1, 2, 3 bonds. But when I look at the math has told me I need 4. So I need to either put a double bond here, here, or here. So sometimes people are like, oh, it doesn't matter, just put it wherever you want. But in this case, it does matter. Okay, the reason it matters, if you think about fluorine, fluorine on its own has 1 empty valence spot, right? So that would say that fluorine generally wants to make 1 bond because it only has 1 bonding electron, okay? Whereas sulfur, if we were to draw the dot diagram for sulfur, right, we would do our S, and it has 6 valence, right? So 1, 2, 3, 4, 5, 6. So it has 2 bonding electrons, okay? This and this are both referred to as bonding electrons, and they're bonding electrons because they are unpaired and they want to pair up with something. These other ones here that are already paired, we tend to call these lone pairs. And that's because they're already paired up, and most of the time we're going to find that they don't participate in bonding. So going back to this question, we are going to draw the double bond with the sulfur. We're going to do it with the sulfur because it has 2 unpaired electrons. So generally, sulfur wants to make 2 bonds. Because the sulfur is only attached to the carbon, it's going to make a double bond there. The fluorine, on the other hand, only has 1 unpaired, so it only wants to make 1 bond. Okay, so now that we've done that, we have 1, 2, 3, 4 pairs, so we have our 4 bonds. Okay, next thing we're going to do is we're going to fill up our valence shell. So we look at this fluorine, it has 2, so it needs 6 more. So we put in 3 pairs. Same with this fluorine, it has 2, it needs 6 more. So we put in its pairs. Okay, we have carbon. It has 2, 4, 6, and 8. So it's not going to get anything drawn on it because it already has a full valence shell. We look at our sulfur. It has 2, 4, so it needs 2 more pairs so that it has 4 more. So we're going to draw a pair and another pair. Okay, so that now gets my sulfur up to 8, right? Because 2, 4, 6, and 8. And we do want to make sure that we draw these as pairs. If you wanted to draw them more on the sides, or like 1 on the side and 1 on the bottom, for now you could do that, but you will eventually see as we go further in the unit that we always kind of want to try to space out those electrons as much as we can, because electrons all have negative charges and they're all going to repel each other, okay? So last thing we want to do is we want to make sure our molecule works. So we have determined that we should have 24 valence electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we have the correct number of dots. Next thing we want to do is make sure everything has a full valence. So that has 8, that has 8, that has 8, and that also has 8. Okay, so things to consider when you are drawing dot diagrams. 1, I highly recommend you don't use pen unless it's erasable, because sometimes you put a pair of electrons in somewhere and then you realize that you don't want them, and next thing you know you're trying to scribble out pen, or you're trying to like white it out. Tends to be easier to do it in pencil or in something that is erasable. Okay, the other thing I would also caution you of, and I am totally guilty of this. I know when I use pencil, I like push really hard on my page. So even sometimes after I erase it, it still sometimes looks like something's there. Really important to make sure that when you are erasing, you actually erase what is there. And if you have a hard time erasing something, maybe put a little note to indicate that those were erased. Because you got to remember, we're counting the dots you have on the page. If you have residual dots that you meant to erase and didn't erase, they may get counted as being there, even though you didn't intend for them to be there, okay? So that is the first way. It's the more math way. I find it tends to be the way that some of you like. I'd say most of you like, but some of you don't like this way, and you're like, I just don't think that way, and that's totally fine. This is where you can use method 2. So for some of you, as I walk through this method, you're going to be like, this doesn't make any sense to me. I liked the other way. And that is totally fine. I'm never going to ask you to specify which way you are drawing it. You just have to be able to know what process you need to follow with the method that you have selected. So once you decide which of the methods is the one that you prefer, I would suggest that you just do both worksheets in that method. You don't have to do them in the method that is outlined on that sheet. They're just outlined that way to show you the 2 different ways, okay? All right, so method number 2, this is more the visual way. So first thing you're going to do, which is the same as the first thing we did in the last method, is you're going to identify what the central atom is, right? So you're gonna figure out what that is, you're gonna write it down, you're gonna place the other atoms around it. You're then gonna determine the total number of valence electrons. And again, that step never goes away because we need to know how many total dots we can have for our diagram. Okay, this is where it becomes different. So we are then going to go to our diagram and we're going to place an electron pair in each bond. Okay, so we start with singles everywhere. Then we are going to go to all our non-central atoms and we are going to fill them up. Okay, we're going to just give them 6 more or 4 more, depending on how many things they're already attached to. And we're going to give them 8 electrons. We're then going to count up how many dots we've drawn. If we see that, like, we've drawn, let's say 20 dots, but we knew we were allowed 24, then we're going to go in and we're going to place those remaining 4 valence electrons on our central atoms. If, though, we see that there are no extras to place, then we're not going to put anything on those centrals. The last thing you're going to do is you're going to potentially have to move electrons. Why I say potentially move electrons is this step might or might not apply, depending on where you are at. And what's going to determine whether it applies or not is, do your central atoms have full valence shells or not? If they already have full valence shells, you're not going to have to move valence electrons to create doubles or triples. But if they don't have full valence and you don't have any more dots left to draw, you're going to have to move electrons because you always have to have a full valence shell on all of your atoms, okay? So what this is going to look like? So this, I want to say, is, I think, the first example off of the worksheet that uses this method. So we need to decide where we are going to draw our atoms. So N has 5 valence, which means it has 3 unpaired. O has 6, which means it has 2 unpaired. So because the N has more, it's going to go in the middle. So in this case, we have a much larger molecule than we have had in the past, right? We have N2O4. So what you are going to find, again, remember how we talked about how our molecules tend to want to be symmetrical, is the N's are both going to be what we call central atoms. So they're both going to go in the middle. And the O's are going to get placed around them, trying to make sure we make something symmetrical. So we're going to put an O and an O. You could also draw them. Maybe I'll move them around. I'll put them above and below. And then we'll do the same thing over here, an O, and then another O. Okay, so that was our first step. Determine our central atom, figure out the placement of the others. Sorry, next step, we need to figure out our valence electrons. So we have 2 N's, which each have 5, and then we have 4 O's, which each have 6. Okay, so from that, we figure out that we have 34 valence electrons. So our steps were to start by placing a pair between each. So there's one pair between the N and the O. Here's another pair between this N and this O. We're going to put a pair between the 2 N's, and then a pair here, and a pair here. Okay, now we've put a pair between all the different sets, okay? So you're not putting a pair between these O's, you're not putting one between these O's because they're not bound to each other, right? Our non-centrals aren't going to bind to other non-centrals. It's just going to be the central atoms that bind to things, okay? So now that we've done that, we are going to put full valence shells on all of our non-centrals. So we're going to fill up the O's, so they each need to get 6 more. So go ahead and do that. Okay. Then what we need to do now is we need to figure out how many dots do we have. If we don't have 34 dots, we're going to be able to add some in on our ends, right? And we know these ends ultimately need more because when I look at this end, it has 2, 4, 6, and same with this one. So if we don't have 34, we're going to be able to place some on the ends. If we have 34, then we're going to have to move some stuff. So let's see what we have. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34. So we already have 34 in our picture. That was how many we said we were allowed to draw, so we don't get to add any more. But that doesn't mean my picture is done because both of these ends don't have enough. So how we're going to fix this is we're going to move electrons. So I'm going to choose a pair off of here. I'm going to take these two and I'm going to shift them to be over here. So I'm going to shift those two there and I'm going to get rid of them over here. Oh, apparently I got rid of one of them as I erased those. So that still leaves the O with 8, right? Because I took the pair that was here and I just shuffled it over to the side. But in doing that, I've now given this end 2, 4, 6, and 8. We have to do the same thing over here. It doesn't matter if you choose this O or you choose this O. I think I'm going to choose this one because I have a little more space down here. So I'm going to move this pair into here, and then I'm going to erase it from where it originally was. So again, the O still stays at 8, but now this N moves up to 8 because I shifted the pair over, okay? So now when I look at it, this O has 2, 4, 6, 8. This N, 2, 4, 6, 8. This O has 8. This O has 2, 4, 6, and 8. My N, 2, 4, 6, 8. And this O has 8. Okay, so everything has a full valence shell. We want to make sure that we have 34 dots. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34. So we have all our dots. Everything has a full valence shell. So some of you prefer this method where you're like, I see dots and I see moving dots. And some of you are like, how'd you just move the dots? Why did you move the dots? Why did we do that? I don't understand why we did that. And it's one of those where it's just something we can do. And that's where if you don't like this way and you're like, moving the dots messes with your head, then go use the math way. Because had I done this in the math way, what I would have found is once I did all of my steps, it would have told me that I needed 1, 2, 3, 4, 5, 6, 7 bonds. And so from the fact that I knew I needed 7 bonds, right, and I'll kind of show you really quickly over here, right, we would have still had this placement. But yeah, from the fact that we knew we needed 7 bonds, we would have gone in, remember, we would have done 1 pair, 1 pair, 1 pair, 1 pair, 1 pair. We would have said, oh, that only gets us to 5. We need 2 more. So I might have said, okay, I'm going to choose here. So that gets me to 6, but now I can't put another double bond here or here because this N already has 8. And if I put a double bond here, then that wouldn't work. So then I would come over here and maybe do that. And then I would see, okay, now I have 7 bonds. This N has 8, this has 8, and then I would have just gone in and been like, okay, we're going to put 6 here, 6 here. The ends, we would have been like, doesn't need anything, it already has 8, and then these O's, we would have been like, oh, it already has 4, so 2 pairs to get it there, right? And this is going to be the same as this. The only difference is I drew the double bond here instead of up here, but really it's the same because it's important to remember that our molecules can rotate, okay? So yeah, 2 different ways of getting ultimately to the exact same picture. Whichever way you prefer, just use that way. Don't try to use both ways. You tend to just confuse yourself if you do that. So whichever way kind of made the most sense to you, I would suggest starting with that worksheet. And then once you feel like you've got it down, go try the other worksheet using that same method. But if you find that you try a couple and you're like, you know what, this isn't really working for me, then maybe go to the other worksheet, try the other method, try a few that way, and see if that makes sense at that point. So the only last example to look at would be something with a charge, okay? When you have a charge, this is going to change something in both methods. What it is going to change is your valence electron count. Okay, if something has a charge, that means you either have additional or fewer electrons in that total valence electron count. So having a 2 negative charge means I have 2 additional electrons. So when I am doing my total count, I'm going to have to add 2 electrons to whichever count I am doing. Okay, so starting off this example, right, we still have to figure out what goes in the middle. So between C and O, C has 4 unpaired, O only has 2. So we are going to put our C in the middle, and then we have 3 O's to place around it. Okay. Again, I kind of went in a triangle. You don't really have to. You could have gone to the top, to the right, to the bottom. Doesn't really matter. So doesn't matter which method you are doing, both methods will require you to determine the total number of electrons. So we have carbon, which has 4. Then we have 3 oxygens, which each have 6. Then we have this -2 charge. So we are going to add 2 electrons to our count. So we're going to do 4 for this, plus 3 times 6 for this, plus 2 from this. So that means we are allowed to have 24 valence electrons in our diagram. So if you are choosing method number 2, you could start to place electrons in bonds and fill up your non-centrals. If you are choosing the math way, your next step would be to determine if I wanted to give all of these a full valence shell, how many electrons would I need? So I have 4 atoms, none of them are special atoms, so 4 times 8 is 32. Okay, then we would get the difference, so 32 minus 24, which is 8, and then we divide by 2 to get 4. So we know that we need 4 bonding electrons. So 1, 2, 3. That's a bond placed. That only gets us to 3. We said we needed 4. So I can pick one of these to put that second one into place, okay? Then from here, we're going to fill up our valence shells. So carbon in the middle already has 2, 4, 6, and 8. It doesn't need any more. My O over here has 2. So 4, 6, and 8. This O has 2. So 4, 6, and 8. And then this over here already has 4. So it only needs 2 more pairs. So we have to do one last thing with this picture. Because it has a charge, we have to draw square brackets around the entire diagram with that -2 charge up here. So kind of like we did with ionics, right? Square bracket with that negative charge. Okay, if you were doing it the other way, kind of did that example more the math way, and that's because most of you guys do choose that way. But if you had chosen to do it the other way, right, you would have gone and put a pair in each location. You then would have gone and filled up valence shells of all the non-centrals. It's a lot of dots. And then you would have counted how many you had. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. You would have seen that you couldn't add any more, but that your carbon only had 6. So you would have picked a pair to move in and erase out of its previous location, okay? And then same deal, you still would have gone and put square brackets around it with that charge of 2 minus, right? So same diagram, just 2 different ways of getting to that diagram. Like I say, whichever way is your preferred method is the one you should use. So one last kind of tidbit, I guess I would say, that some of you guys struggle with is in your final diagram, you should never have an unpaired electron. If you have an unpaired electron, something doesn't work with your picture. If you have 2 unpaired, it's probably because you should have paired them. If you have a single unpaired, something's gone wrong in your count. Either in your diagram, you're missing one and it should be paired, Or here, when you did your number counts of how many valence electrons, you miscounted the number, and you need to go back and double check that, because everything should be paired, everything should have a full valence shell, and you should have the exact number of dots as valence electrons you have calculated at the beginning of the question, okay? So really important to make sure that you can do these covalent diagrams, because like I mentioned, everything we do pretty much in the rest of the unit builds off of being able to draw these. So you'll have to draw this to do the next thing, and then you have to be able to do those two things to do the thing after that. And it just kind of keeps building. So really important to make sure that you have this piece down, okay?